Here we go. Okay, now listen. I want you to, I kind of want to preface this just by saying, I want you to understand something, that as you move further along in math, it begins to change. Like when you learned grade school math, adding, subtracting, multiplying, dividing, it was, here's a skill, put it into practice. Here's a skill, put it into practice. Even really like sort of pre-algebra stuff, it's like, here's a skill, put it into practice. Like here's how to graph a line, put it into practice. But as you move further along, it becomes more about the context. It becomes more about the bigger picture. And what I want to do for you guys in this class is I want to give you a deeper picture of geometry. Not just here's some skills with some shapes, put them into practice, but more, how does this fit in the big story of mathematics? And for us in this class, there's a really rich background, which I already started with you, in the history of mathematics. And of course, the stuff that we've been doing, some of it is 2,500-year-old math. You're going to see language that you may have already heard today that comes from 2,500 years of use. Well, that's kind of interesting when you think about it from that perspective. And so please just understand that what I'm trying to do here with you is, I'm not about getting through it as quick as possible. That's not my goal. My goal isn't just to say, here's a skill, put it into practice. My goal is, here's what geometry is. Here's the whole context. I want you to see it for what it is. And then we can take it and really expand it out and make our skills shine. That's the goal of what I'm trying to do for you today. So just kind of keep that in mind as we're working through this. Okay, so we are continuing along with our Euclid's definitions. Right now, he had started off with a point, was a thing that had no part, it had no measurements to it, and then we got into these ideas of lines, and we talked about how modern geometry breaks lines into segments and rays, depending on whether they extend infinitely in both directions, or they have, finite in both directions, or finite in one and infinite in the other, right? And so now we're moving into the next level, right? So we have now what we call surfaces. Okay, so a surface is that which has length and breadth only. Now keep in mind, and I don't know if you have your notes in front of you, but I'll just say, like the previous notes that we had, it was a line is breadthless length, or I had said widthless length. It was one dimensional or one measurement, right? It was just the length measurement. Well, now you can see that we're getting length and breadth, which is another word for width. And so what we have are two dimensions that are popping up here. So a surface has opposing measures. Okay, these are opposing measures called length and width, which is what Euclid meant when he said breadth. So therefore, surfaces are now two-dimensional. So now I've had no dimensional, one-dimensional, and two-dimensional. All right. Now I'm going to give you a drawing that I want you to draw on your paper. First, we'll start with that, and then we're going to kind of build into it. So let me get that for you with this right here. So let's start with this drawing right here. So if you could make these two drawings on your paper, I'll give you about a minute to get that done. All right. So go ahead and make those. Now, as you're drawing these, I'm going to kind of add to this picture and talk through these a little bit. So, as I said, a surface has opposing measures called length and width. So, I'm just going to do a little L down here. I'm going to do a little W over here, length and width. You can see these are opposing because they're not in the same straight line. And so, surfaces, in their most general sense, like lines, extend infinitely. This time, I would, instead of saying, they extend infinitely in all directions, really, both directions, length and width, right? And so what I'm going to do is I'm going to draw a couple like arrows just sort of coming off of here like that and down here like this. And so there's this idea of our plane sort of our surface extending out infinitely in both length and width directions. Now, surfaces can be flat, or they can be curved. And so this is what I have for you with these other two pictures. So watch what I do up here with these other two lines. I'm just going to kind of do a little swoop. See how I did right there? It's like a little curved swoop. I'm going to do the same thing on the bottom. I'm just going to do a little swoop like that. And so it's almost like if I took a piece of paper and sort of bent it, kind of like this, I could have sort of a curved surface. I still have two dimensions to it. I have this dimension and this dimension. So it's still two-dimensional, but it's okay that it can be curved. And again, these would extend infinitely in all directions, like that. So this is our initial layout of our two-dimensional shapes, which are called surfaces. Now, the edges of a surface are lines, Euclid states in his sixth definition. All right, and he says the edges of a surface are lines. So similar to how finite lines, we call segments, have endpoints, finite surfaces have ends that are segments. And that would be like, like if I come back up here to this example up here and I put a point here and a point here, or even if I put a point here and a point here, you can see that I've created a finite segment, which is an edge to my surface, or even a curved finite segment that is an edge to my surface, right? And so that's what we've got going on. Now see the connection, right? We had points, and then points made the ends of lines, and now lines make the ends of surfaces. See how this works? Okay? And so it's kind of a progression as we're working along here. All right, so let's continue with definition 7 here now. Now he says, now he's going to kind of clarify this a little further. So we've said now a surface is a two-dimensional length and breadth, right? So then he goes on and he adds this word, a plane surface. Okay, this is not plain like I don't want anything on my hamburger plane. This is plain like flat, which lies evenly with the straight lines on itself. Now, if you think about our definition for a straight line before, was it lied evenly with the points on itself. Now we've got a surface that lies evenly with the lines on itself. Again, that progression of moving through is what we see happening here. Okay? All right. So when we are referring to a flat surface, so now we're leaving curved surfaces behind, and we're going to refer to flat surfaces, we use the word plane. So when we talk about the word plane, P-L-A-N-E, we are talking about a flat two-dimensional surface. Sometimes it's plane surface, just like you see in the original definition. Most of the time we just talk about it as a plane. All right, let me give you a couple of pictures to start off with here. So I want you to draw these two shapes, the sizes you see, the positions that you see. Try to get those two as a starting place for us to work with on our paper. Go ahead and draw in those two examples. I'll give you about a minute to get that done. All right. So planes, now let's talk about how we name planes. Just like we had to name lines and segments and rays, like on your last test, right? You had to have the right symbol above 2 letters, because it's always 2 letters, 2 points to name a line, segment, array. Hopefully that's what you put on your test. Okay, so planes are named with 3, watch this, non-collinear points. Planes are named with 3 non-collinear points. Wait a minute, you just had a question on your test about collinear points, right? What are collinear points? Anyone got collinear points? Okay, points that sit on the same straight line. So now we need 3 points that cannot sit on the same straight line. So that might look something like this. On our first picture here, I want you to put a point here. Let's call that X. And then I want you to put a point up here, and let's call that Y. And then I want you to put a point over here, and let's call that Z. Okay, now, what you should be able to see here is that I can draw a straight line through any 2 points. We've learned this already, right? So if I wanted to, I could draw a straight line, and you're not drawing these, I'm just showing you. Okay, I could draw a straight line through X and Y. That's one thing I could do, right? Also, I could draw a straight line through Y and Z, right? What I cannot do is draw one straight line. Hang on. What I cannot do is draw one straight line. Hello. There we go. One straight line through points X, Y, and Z all at the same time. That's why I have to have 2 dimensions to contain all 3 of those non-collinear points. So I need both dimensions or a flat surface to contain 3 non-collinear points. And that's what forces me to have a plane. So if I were going to name this, I would name it like this. I would say this is plane. I'd actually use the word plane, and then 3 capital letters, X, Y, and Z. So this is plane, X, Y, and Z. Now, I had mentioned to you previously that sometimes we can name a line with like a little lowercase letter off to the side of the line. Well, for planes, we can actually name it with a capital cursive letter. And that's usually just kind of found in like the upper corner. So I'm going to do like an R up here. And so I could say, or this could be called plane R like that. Again, that's a little more old school, but you might see it, so it's worthwhile to know. Okay, so here we can say, watch this, points that sit on the same plane are called coplanar points. So now I got collinear points, they sit on the same line. Coplanar points sit on the same flat two-dimensional surface. So here we can say that X, Y, and Z are coplanar. Elsewhere, we're gonna do something above this other shape. So write this down here, coplanar. Okay, not complainer, coplanar. Okay. Now I want you to notice this one. So just like we had collinear and non-collinear, we can have coplanar and non-coplanar points. Okay. Now, if we had non-coplanar points, think about what that means. Coplanar points lie on the same flat surface. And we need to have 3 of them in order to contain that flat surface, right? If we had 2 of them, we could draw a line and contain them and we'd be good with a line. So we have to have a minimum of 3 points to force us to have a 2-dimensional surface. So then if we have non-coplanar points, we've got to have a minimum of 4 points. You say, well, why 4? That seems weird. Well, let's do this. Let's recreate the same plane we just drew up here by doing a little point X and a little point Y and a little point Z. Little point X, little point Y, little point Z. But then let's do this. Starting at this corner right here, I want you to draw a little line going back like that. And then I want you to draw another line, the same, going back like that. And then let's draw a line going across like that. And then let's bring another line down like that. And lastly, let's connect these 2 points down here like that. And then let's come out here and let's put a W. Now we have 4 non-coplanar points because you can see that W sits on a different flat 2-dimensional surface than X, Y, and Z. Do you see why? Okay, so we can now say down here, X, Y, Z, W are non-coplanar because they don't sit on the same flat 2-dimensional surface. There's no way that I could position a flat 2-dimensional surface to encompass all of X, Y, Z, and W, which means I need how many dimensions? 3 dimensions, and it continues to grow. See, now we went from no dimensions to 1 dimension to 2 dimensions, and now we're into 3-dimensional geometry, or what we called solids originally, the Platonic solids. Remember, I showed you those. Okay, so this is the idea of surfaces, but this is not really the focus of what we need to do today. This is just sort of the next thing that Euclid kind of lays out in his definitions. So let's get into the meat of what we have to do today, which are definitions 8 through 12. Let's get into the meat of what we have to do today, which are definitions 8 through 12. All right, we're going to start by saying this. Definitions 8 through 12 establish how the word angle, a key concept in geometry, is used. All right, so let's talk about Euclid's definition here. First off, you can see that he says a plane, just talk about that plane, flat two-dimensional surface. A plane angle is the inclination to one another, sounds like a relationship word, huh? Inclination to one another of 2 lines in a plane which meet one another and do not lie in a straight line. Huh? Okay, all right. Well, let's break it down. That's the whole goal of this, right? My goal is to help you understand what it is that he's trying to say here. All right, so let's do this. Okay, the term plane angle again, flat two-dimensional surface, angle, is used to describe the way two lines which intersect each other, they meet, they cross, they touch, okay? It's meant to describe the way these two lines intersect with each other on the same flat surface and how they incline, lean, or slant toward one another. How's this relationship of how they lean or slant toward, or in some cases away from, each other? That's what we're going to be talking about. So this is this idea of a plane angle. All right, I'm going to give you a picture to draw here in just a second. So if you want to grab your compass out, this is where you're going to use your compass. Here is the picture that I want you to draw. Use your straight edge and your compass to create this picture in here, all right? I'll give you about a minute to create this picture. Grab one of your colors, and here's what we're going to do. I'm going to color in here like this, just kind of get that colored in. And so we have a curved line and a straight line, and they are related to each other in a sort of way. You can see this, in this case, what I have highlighted here is how these lines incline or slant or lean toward each other, okay? And so this in here is what we would call a plane angle. Now, maybe if I had said to you the word angle, if I had said to you earlier, before we started class today, draw me an angle, I'm not sure how many of you would have actually drawn this picture for me right here. But that is what we call a plane angle. Now, modern geometry would describe this leaning toward, or in some cases, again, like I said, you'll see leaning away from, as the space or gap that exists between our two lines. So we've got our curved line, got our bottom line, and as they lean toward each other, what I highlighted in green is what we call the angle, the plane angle. That is the space in between the lines. That's how you have to understand what an angle is it has to do with the space in between the lines. Now, lastly, this particular definition is limited in that the lines cannot intersect in such a way that they make one straight line. They cannot in the way that they make one straight line. And essentially, you're not drawing this, I'm just going to show you, but essentially what Euclid is saying here is if I took a straight line like this, and then I took another one like this, a plane angle would not be where I took this line and then joined it together here. That would not be considered a plane angle. Now, we are going to see that where we have two line segments joined together like this, but that comes later in his propositions or his proofs. That's something that he proves is possible, not that is a stated definition. And so that's important to sort of keep that in mind, that we're talking about different things here. Okay. All right. So this is a plane angle. All right. Now, definition 9 refines the understanding of the space between any two intersecting lines, okay, whether they're curved or straight. And so let's read definition 9. So definition 9 says, and when the lines containing the angle are straight, okay, before they were curved and straight, that's the example I gave you. Now we're saying when that space contained between the angles, those lines are straight, that angle has a special name. It has a very specific name. And that specific name is for the straight lines that contain the space. And it's rectilinear. Rectilinear. It's literally translated straight line. Recti is straight, linear is line. And so the literal translation of a rectilinear angle, as opposed to a plane angle, is one that is contained by straight lines. All right. So let's draw a picture of what this is going to look like. So let's just take, and we'll draw a line out here like this, and then we'll draw another line out here like this. And then let's take the space in which those lines incline toward each other in here, and let's just kind of color that like that. This space in here now is called a rectilinear angle. And so being able to spot the difference between a plane angle and a rectilinear angle would be the difference between whether there's curved lines involved or just straight lines. Catch the difference? Okay, rectilinear angles, space in between two straight lines. Plane angle, space in between any lines. It'd be like if I said to you, you know, all Mustangs are cars, but not all cars are Mustangs. Huh? Right? All rectilinear angles are plane angles, but not all plane angles are rectilinear angles. Oh, see what I'm doing? It's more like a classification. It's a refining of, okay? Now, even more so, modern geometry has further defined the parts of a rectilinear angle. Watch this. This is super important. This is where it gets really important. By giving names to the parts, specifically the lines that form the angle, the space in between. Those lines are called the sides of the angle. And watch this. The point of intersection of the straight lines is called the vertex. This language starts to develop in early modern Renaissance time. We start to see this popping out. So let's label up some things on our picture here. So this is a side. This also is a side of our angle. These two lines are considered the sides of the angle. And if we just put a little point down here, just to emphasize this, I'm even going to circle it. This is what we call the vertex of the angle. Now, there's some really important language here that you need to pull away from this, right? Okay, I'm going to speak some geometry to you. Let's see if you can understand what I'm saying. You ready? The space in between two lines is called an angle. If those two lines are straight, it's called a rectilinear angle. Those straight lines are the sides of the angle. The point where those two straight lines meet is the vertex of the angle. Did you understand what I said? Yeah. Good. You're speaking my language then. That's awesome. Okay. All right. Good. Let's keep doing. Let's keep refining here. Here we go. All right. Now watch this. Definition 10. There's a lot in this definition, okay? But what this does is it marks a turning point for us. Okay? Definition 10 marks a turning point by defining concepts through a comparison of angles. Okay? Defines concepts now through a comparison of these spaces in between these lines. Okay? Now, I'm going to read it to you. Again, there's a lot in here, so we're going to kind of break it down. So here's definition 10. When a straight line standing on a straight line makes adjacent angles equal to one another, each of the equal angles is right, and the straight line standing on the other is called a perpendicular to that on which it stands. That's a lot. There's a lot in there. So let's kind of break this down just a little bit. Okay, first off, the word adjacent. This is going to be a really important word for us this whole school year. All right, when we talk about adjacent things, we can really use this sort of generic definition of next to, right? So adjacent angles are next to each other, or specifically, we would define them in math languages. We would say adjacent angles share a common side. Adjacent angles share a common side. Think about what that means for a second. That means that one of the sides of the angle is the same in both of them. Okay? All right. Let's get sort of a picture rolling here. I'm going to give you a picture that I want you to draw here. And this will actually kind of serve as a counter example. Again, you're going to draw this drawing here in this area of the example box. I'm going to start doctoring up this picture just a little bit. So here what I want you to do is I want you to color in this space over here with one color. And then I'm going to use a different color to color in this space over here like that. Now keep in mind that I have two angles here, a blue angle and a green angle, because I have space contained by two straight lines. So I have two rectilinear angles here. But check it out. The sides for the blue angle are here and here. The sides for the green angle are here and here. What you should have noticed is that in both of those angles, there is a common side. That's the definition that makes the blue angle and the green angle adjacent to each other. Okay, so let's write that down. These are adjacent angles. Okay, so they're next to each other. They share a common side. They're like next door neighbors. Okay? All right, now, you'll notice that here in Euclid's definition is he says that when you have this situation where adjacent angles are equal. Okay, let's talk about this for a second. So the concept of equality here is what we would call a qualitative assessment. It's a qualitative assessment, which means it's non-numerical. Notice I haven't used any numbers. This is a non-numerical assessment of equality, and it's made empirically through experiment or observation. So it's qualitative in nature, and it's made empirically. In other words, we can all pretty much agree by looking here that the space defined by the blue color is clearly smaller than the space defined by the green color. Would you agree with that? Okay, so we could say that the blue space and the green space are not the same. Would you agree with that? Okay, or we could say, more mathy, we could say they are unequal. Would you agree with that? So blue and green angles up here are unequal but adjacent angles. Would you agree with that? Okay, we just made a qualitative assessment without any numbers whatsoever. See how we did that? Qualitative, empirical assessment. All right, so we can say this. These are non-equal adjacent angles. Okay, but that's not what Euclid's defining in his 10th definition. He's saying when adjacent angles are equal. Okay, well then we need a picture for, if this is a counterexample, if this is non-equal adjacent angles, what would it look like to have equal adjacent angles? Okay, here's what I want you to draw next. You have this picture in your mind. Okay. All right, now I'm going to color in the left side blue, and then I'm going to color in the right side green. Okay, so empirical assessment, qualitative empirical assessment. Is blue the same as green? What do you think?
I think so. Just about.
Yes or no? Pick a side. Do I have a purple magnet or not? Pick a side, right? Yes or no? Okay, yes, we think. Why? What's something that we could, how's some way we could check that?
Squares. The right angle sign.
I don't see any right angle sign symbol up there.
Oh.
Gianni? We don't have any measuring tools. We don't have any quantitative way to put together measuring. Loja? Okay, they kind of look even, right? What if we took some tracing paper, let's say, and let's say we traced over the blue one, and then we flipped it over onto the top of the green one. If they were the same, they would line up, right? We used that word before. In fact, that was a common notion or an agreed upon mathematical principle that everybody coming into this said, we agree with that. Yeah, that's going to work. And so the word was coincide. Since the adjacent spaces between the lines, watch this, coincide, sit on top of each other, common notion 4, see I put it right there, that would make the angles congruent. Figure language. Right? So we can use our figure language here, and now we can say that we have congruent adjacent angles. We have congruent adjacent angles. Now, when we have adjacent angles that are congruent, Euclid defines those with this word. He calls them right angles. So, right angle. If I said to you, what's a right angle, you might be thinking of a certain number in your head. But we haven't talked about any numbers. There are no numbers here. So what I really want you to have in your head is when I say, what are right angles? You're going to say two congruent adjacent angles. See the difference? That is a qualitative assessment of right angles, as opposed to quantitative. We're so used to working with numbers, and we're going to do plenty of number working, trust me. But right now, we're working qualitatively or synthetically. See the connection? Okay? All right. Now, we do, in modern geometry, use a particular symbol to confirm, without numbers, that these two angles are, in fact, right angles. And we put this little symbol in here. And when you see that symbol, this is our right angle symbol. We only need to put it on one side. Because when I say that this angle is a right angle, by definition, it must have an adjacent angle equal to it. See what I'm doing there? Okay, so by putting one right angle marker, by definition, I'm saying that means that the angle adjacent to it must also be equal or the same size. Okay, now watch this. Since there's only one way for two lines to intersect where adjacent angles are equal, hit the brakes. Wait, what, Miss Vargas? There's only one possible way? Yeah, check it out. Watch this. You're not going to do this, but I can do this because I have cool little digital tools. But watch. Let's say I took this line up here. Check it out. I could move this line like a gauge all the way around. Those are adjacent angles. Those are adjacent angles. Those are adjacent angles. Those are adjacent angles. There's only one way that I can position this line like that to get equal adjacent angles. See that? So we can have tons of different adjacent angles, but there's only one way we can have equal adjacent angles, okay? And so that particular inclination, which is the way that these two lines sit in relationship to each other, is said to be this word, perpendicular. I'm going to expect you to know this word and use it all the time. So let's just label our lines with little lowercase letters. We'll call this line L and this line M. And then down here, I can say that lines L and M are perpendicular to each other. Lines L and M are perpendicular to each other. Okay? So when I use that word, you should understand that that creates two congruent adjacent angles. Perpendicular lines create two congruent adjacent angles. Or if you have two congruent adjacent angles, those angles are right. Or if you have a right angle, it is formed by perpendicular lines. Did you understand what I just said? Yeah. Speaking a lot of geometry to you, understand how all those words interplay together is going to help you be successful. Okay? All right, so now we've got these adjacent equivalent angles, these right angles by definition. Now we can talk about some other relationships that exist. Like, for example, this one. I'm going to give you the picture to draw first. All right, go ahead and create this picture here on your paper. And while you're creating this picture, I'm going to do a little coloring too, which you can also do as well. So I'm going to color in here with my one color. And then I'm going to color in here with my other color. And I'm going to add this to my drawing here. See what I added there? Now the green, empirically, looks pretty obvious that it's bigger than the blue, and so we call that an obtuse angle. 2,500-year-old word. There you go. Didn't realize you were using that old language, did you? Okay, so this one would be considered obtuse because it is greater than what? Greater than what? No, don't give me any numbers. I don't want to hear any numbers. We're doing synthetic geometry. No, that's not adjacent. A right angle. Thank you very much. Exactly, right? We're not doing numbers here. We're not doing analytic geometry. We're doing synthetic geometry. Okay, I'm going to give you the next picture to draw. All right. Here's your next drawing. Very good. Yeah, so I'm going to color this one color, and then I'm going to color this one again, another color here. And I'm going to add this symbol in here. So green, empirically, as I look at it, very clearly less than the blue space. Does anybody know what we call this one?
Acute.
This is an acute angle. Again, another 2,500-year-old word there for you. So this is what an acute angle looks like versus what kind of an angle? A right angle. Very good. So again, just like we started in definition 10, we're defining concepts based on comparison, right? We're comparing adjacent angles. Are they equal or not equal? Now we're comparing sizes of angles. Is one bigger than a right angle? Is one smaller than a right angle? That's how we're defining obtuse and acute, right? From a synthetic standpoint. Okay? And now on to our last section. We're almost done here. Okay, now, we've talked a lot about the history of mathematics, and one of the biggest things that happened in history was the invention of the printing press. This changed education, because before the printing press, it was a person standing up front telling you everything, and you had to just kind of listen and maybe make some notes for yourself. But then, when textbooks became a thing and everybody had the same instructions and the same pictures and the same everything in front of them, that changed things. And one of the things that it changed for mathematics was the development of what we call mathematical conventions. Okay, mathematical conventions. Conventions. Mathematical conventions. And these are not gatherings of mathematicians. Not that kind of a convention. These are commonly accepted ways of doing things. That's what we call a convention. A commonly accepted way of doing things. Like, for example, when you want to multiply x by the number 2, you don't write x2, you write 2x. That's a common mathematical conception. Well, another one is naming angles. And this is really the crux of what you need to pull away from this lesson from a practical standpoint, is how to properly name these spaces. Because right now, I've been saying blue and green up to this point, or on the left or right, or this one or that one, but we want to be more specific. How can we name these things within a diagram? Okay, so here's how we're going to do it. In modern mathematics, okay, don't lose this point. Stay focused, Cooper. Here we go. In modern mathematics, angles are named using 3 points. Angles are named using 3 points, or 3 capital letters. Okay, and those 3 points or 3 capital letters are preceded, that means comes before, are preceded by the angle symbol. Okay, if you want to put a little color highlight around that, that is so important when you're naming your angle. You're going to use this angle symbol. All right, now here's some rules for these 3 points. The first point in the name is on a side of the angle. You should know what that is now. We've covered that. The middle point in the name must be the vertex of the angle. And the third point is on the other side of the angle from the first point. So you've got 1 point on a side, 1 point the vertex, and 1 point on the other side. And what this does is it helps us identify these different angles when multiple angles share the same vertex. This helps us identify when multiple angles share the same vertex, how you can communicate what space between what two lines are we talking about. Okay? So let me get you your next picture you're going to draw. You want to keep this up towards the top of your box. On your additional examples, I want you to draw this picture that you see right here. And I'm going to add some things to this picture while you're drawing it. So first thing I'm going to add is I'm going to add a little point right here where those lines meet. And I'm actually going to give that a name. I'm going to call that D. And while I'm at it, I'm going to add a point out here, and I'm going to call that A. Up here, I'm going to add a point. I'm going to call that B. Over here, I'm going to add a point. I'm going to call that C. And down here, I'm going to add another point. I'm going to call that E. And then I'm going to put some arrowheads on my straight paths to indicate that they continue moving in those directions. Now, this could be a question that I gave you like on the last test. Name for me a ray. Name for me a line. Name for me a segment, right? Like, I mean, that's what we see here, right? And so within that same picture, we have the straight paths that you were naming previously. Now we've got to name the spaces in between them. Okay, so like if I said with this one, let's say I'm going to color this one blue. And then I'm going to do a little blue swatch over here so I know what I'm talking about. If I wanted to indicate that space in between those straight paths right there, I could say, hey, I'm talking about angle ADB. See what I did? I used the angle sign. I picked a point on a side. I went through the vertex and out to the other side, ADB. Or I could call that angle BDA. Was that your question? Yep, exactly. Because all I have to do is start on one side, go through the vertex, and just go out to the other side. So either way, if you say to me, hey, Fargus, I'm talking about angle ADB or angle BDA, I'm going to know what you're talking about because that is the space contained by segments BD or ray DB and ray DA. See how that works? Okay. Now, likewise, let's say I wanted to talk about this space in here. I could do a little green swatch over here to indicate what I'm talking about. So then in this case, I would say I'm talking about angle BDC or what? Or angle CDB. Either one is fine. Let's color this a third color out here. And I'll put a little yellow swatch down here like this. Why don't you write right here 2 different names for the yellow space on the paper? Go ahead. You write the 2 different names. Go for it. Put angle EDC or angle CDE, right? Those are the 2 different names, yeah? Good. And see, and what's nice about this now that we have this down is I could pick any combination because you know what? There are more angles up here than just blue, green, and yellow. Like I could say, hey, why don't you tell me about that obtuse angle? How would you name that one? Okay, let's write that one down. So this could be angle ADC or angle CDA, right? And so then I could say to you, hey, give me the name of an acute angle. Give me the name of an obtuse angle. And if there happened to be a right angle in there, I could say, give me the name of a right angle. And now you can properly identify those angles. Everybody good so far? Okay, last thing to talk about today. Give yourself a little squiggle here. Now you'll notice down the bottom here I put a special note. When a vertex has only one angle one inclination, one space in between these lines associated with it, it can be named with one point, but that point has to be the vertex. So let's talk about something that looks like this. Why don't you draw this picture here? And I'll put a couple of arrowheads, and I'm going to put a point here. I'm going to call it S. I'm going to put a point here. I'm going to call it R. Point down here. I'm going to call it T. I'm going to shade this in here blue. So I'm giving myself a little blue swatch over here. So this situation is, you can see that I only have one angle associated with the vertex S. And so in this case, it's okay to call this angle S. Okay? Now, again, we could say that we could use our 3-letter naming. So we could say angle RST or angle TSR. But the important thing for you to understand here is that a single angle on a vertex can be named 3 different ways, with just the vertex or with the 3-letter naming. But in a situation like this, you must use 3-letter naming. Because here's why. Look, you can't say to me, hey, Mr. Vargas, I'm talking about angle D. Which angle D are you talking about? The blue angle D, or the green angle D, or the yellow angle D, or the red angle D? Which angle D are you talking about? You have to be specific and say, I'm talking about angle BDC, and then I know you're speaking of this angle here. Okay, you get the idea? All right? Naming angles is so important for you to be able to identify the right thing and tell me the name of it, or vice versa. If I tell you, hey, I want you to do this with this angle name, know what I'm talking about in the picture. Okay? All right, like I said, the good news for you is that homework is super easy. You have one IXL, and you're going to be naming angles and identifying points, whether they sit inside an angle, on a side, are the vertex, or sit outside of an angle. Really simple. And I'm not even going to make you do it right now because you guys worked hard at our notes today, so good job. But you do have one IXL to do. It'll be posted on Google Classroom. Okay? All right, good job.